afternoon, everyone. Welcome to my seminar. First of all, I would like to thank Professor Kawashima for the invitation and giving me this opportunity to present our research work. And actually, this is my second time to visit ISSP. My first visit here that was back to 2005. That visit was also hosted by Kawashima Sensei. Actually,
it was 2006.
No, 2005.
Okay.
Also around this season, I think.
I see.
Yeah. So I'm very happy to be here and participate in this summer workshop. Today I would like to introduce you recent work on the topological quantum phase transition. This Gapless, the title of my talk is Gapless Coulomb states emerging from self-dual topological tensor-network states. This work is based on a recent published paper on PRL, and this paper. So let me first give you a brief history of Z2 quantum spin liquid. The quantum spin liquid was proposed in 1973 by P.W. Anderson. He proposed RVB states to describe frustrated quantum magnet. In particular, this RVB states can be regarded as a apparent compound of high temperature superconductivity. And after that, Kiverson, Roxa, Tsinghua proposed a quantum dimer model, and they found the deconfined soliton in short-range RVB states. And after that, Xiaogang-Wen in 1991 used parton construction to write a mean field Hamiltonian plus gauge fluctuation, and then he gave a Z2 deconfined phase. Previous work, approximate work, only up to 1997, Kitaev proposed exact soluble model, so-called toric code model, to explicitly show the presence of a Z2 quantum spin liquid and also the elementary excitations in these states. After that, Kitaev also proposed a honeycomb lattice, spin 1 half honeycomb lattice model to get non-abelian Z2 spin liquid states. And after, there's another work related to these Z2 spin liquid is this Mosner and Zondi work in 2001. They used a numerical method to show the quantum dimer model on a triangle lattice can have Z2 quantum spin liquid states. So let me first give you a preliminary introduction of this Kitaev toric code model. And you see, this is the model Hamiltonian of the toric code. There are two terms. One is this sum over star size of A operator. The A is the sigma x, the product of sigma x operator around these vertices. And the second term is this BP phase, the BP operator, which is a placate operator. So this the reason why this model can be exact solvable because every term in the Hamiltonian, in this model Hamiltonian, are communicated to each other. So you can easily see that this is an exact solvable model and also the simplest model to show the Z2 spin liquid, the Z2 topological phase. Actually, this model can also be looked at as a minimum discrete Z2 gauge model, which is also an effective model for superconductivity. And this model, what the important things of this model are due to they have anionic excitations. There are three types of anionic excitation. One is called electric charge. This, the electric charge sitting on the vertices. And another excitation called magnetic flux is around the fluctate. And the third elementary excitation is the so-called the bound state of electric charge and the magnetic flux. They call the fermion, fermion states. And the electric charge and the magnetic, both electric charge and the magnetic flux behave like a bosonic operator. And however, if when there are when there are magnetic and when you move one electric anion or make a circle around the magnetic flux, you will get a non-trivial phase indicates the mutual statistic between electric charge and the magnetic flux are semiotic statistic instead of the same and another important property of this model is the so-called electric-magnetic duality, which means when you switch sigma x to sigma z, vice versa, and change the lattice, the vertice size and the placate center, so this model doesn't change, which this transformation actually make the electric charge and the magnetic flux switch each other. So we call this is a electric-magnetic duality, which is quite important for this Topological model. So actually, this kind of model is not completely new in literature because many years ago, a lot of groups studied another model which is just more general model than the Topological model. For example, they introduced the external fields term. For example, Hz field or Hx field. This total Hamiltonian, the whole Hamiltonian, actually is the so-called Z2 gauge Higgs models. This model has been studied many groups by many groups back to early 1980s. You see, but this model is not exactly solvable, but they only can be used, Monte Carlo method to and try to understand the the possible phase transition in these Z2 gauge Higgs models. The main result is about this phase diagram for this quantum model. You see here, when you just look at this phase diagram around horizontal direction, this is HZ field. When you increase the HZ field, you will have a quantum phase transition. This phase transition can be regarded as E-anion condensed phase transition, and similarly, when you introduce a HX field, increase it, you can also have a quantum phase transition. This phase transition actually is due to this electric charge condensing transition, which precisely as a magnetic flux condensed phase transition. So these two quantum phase transition can be understood by the anion condensation scenario. I think the main difficulties is around this region. In this region, actually very close to the self-dual, this is self-dual line, and from the earlier study on this Z2 gauge Higgs Hamiltonian study, they found there's a first order transition line. Actually, this first order transition line will meet these two continuum phase transition line, but people don't know how they connected each other, whether there's a tri-critical point or not. You see this paper. This paper is a 2008 paper, including Kitaev. They say around this tri-critical point, from the numerical calculation point of view, you cannot see how these three lines connected each other. For example, they can such kind of three different scenarios. So, although the numerical calculation has already very intensive numerical resources, this Monte Carlo calculation on the 16Q lattice size already quite large. So there's a most important issue around this region, because naively you will see maybe this electric charge and the magnetic may be combined and form some kind of bound states, and then these two continuum phase transition line continuously smoothly connected to this first order line and forming this tri-critical point. But however, if you think carefully, you notice that this electric charge and the magnetic flux, they behave, that the mutual statistic between them are anionic statistic. So they cannot form the condensing state, or so the physical mechanism of the phase transition around this point is not quite clear, and also a long-standing puzzle in this field. Actually.
I have a question.
Yeah, please.
Why does there have to be a first order transition at all?
The first order transition around this line is the quantum Monte Carlo result.
So it doesn't have to be there, it's just there in this model?
Yes. Because there's another, maybe there's a reason can be understood why this first order. Because this electric charge condensed phase and the magnetic flux condensed phase, both phases are topological trivial. So in the beginning you don't expect there is a continuous phase transition. If there is phase transition, there should be first order.
You might have thought of this. You can avoid the first order line, right? You can go smoothly between the two phases.
But in this model, Hamiltonian got only two tuning parameters. Of course, if you introduce additional interaction term, and you may avoid this first order phase transition.
Maybe I'm misunderstanding, but in your model itself, I think you can...
Oh, this is not all model. I haven't talked about my model.
No, but in this model, I think you can go smoothly from one phase to the other. You can you can go around the blue line, right?
No, you cannot. Because you see this, the first part of this model is a Topological model. There's no parameter in this. And when you introduce two different magnetic field, you only have two parameters, which corresponding to the horizontal line and the vertical line in this phase diagram. So there's no alternative way to get around this first order transition.
What if you go around the perimeter of your plot?
No. This is just zoom in this region, you know. So this is not a phase the transition line. It's just a symbol to zoom in this region, and these people say numerically, actually, you cannot see this three line. How these three line connected each other numerically.
Maybe the related question is the first order transition line terminate at some point or extends to infinity?
Yes.
Extended to
Yes,
infinity.
extend infinite. Yeah, that's right. So, please.
This diagram, as I remember, was for Topological, showing the transition and topological order and the other phases in P-type module Topological. Is it right? Is it
Sorry, I don't quite
the
get
diagram
it.
at the left side of the slide? Yeah. In the inside, like the
the inside this
topological order.
topological order.
Yeah, and the other, and you're talking about and your the phase transition from topological order to others.
Yes.
Or you're just mentioning the existence of electric or charge particles. You transition between.
The transition between this topological order phase and this trivial phase. This trivial phase is
it will be second order.
is second order.
Yeah.
It's second order phase transition.
Yeah.
Yeah.
So.
What? So
Uh,
what's your question?
You may proceed. I'll ask my question afterward.
Okay. So the first question we would like to answer: what kind of a phase transition occur out of this Z2 topological phase along the electric magnetic self-dual path? So this the first question we would like to address. Before that, previously a lot of work has been done, but the puzzle hasn't resolved. So for us, in order to solve this puzzle, we should have found an alternative way to approach this problem. the method we would like to propose is the wave function approach. As you know, in one-dimensional case, we have a famous Affleck-Kennedy-Lieb Tasagi valence bond solid states for the Haldane phase, which quite successful to describe the topology of the Haldane gap phase. Namely, the non-triviality is on the edge of the Haldane chain. There is a spin fractionalization, meaning this spin 1/2 degree freedom come out of the spin 1 system. So this is a famous this is a famous work in one-dimensional system. In two-dimensional system, there's a more famous work done by Bob Laughlin. He proposed a wave function to describe fractional quantum Hall state. In particular, 1 over m. M is the old Feeling fraction first Landau level. This is quite successful and also Nobel Prize work. So if you still remember Laughlin wave function, you maybe know that if you look at the norm of the Laughlin wave function, you can write that the wave function norm into a statistical Boltzmann weight. And you found that this wave function equivalent to a two-dimensional classical model with there's a Coulomb gas system with logarithm interaction form. So this is very important feature of the Laughlin's wave function, and you can get many important information from this 2D classical Coulomb gas. Get a lot of result about the fractional quantum Hall from this 2D classical Coulomb gas system. And also people believe that the Laughlin wave function actually, although it's a ground state wave function, is a minimally encoding all the topological data in this wave function. So from my point of view, the wave function approach may be more important, in particular to study topological phases. So let's come back to our model. Our model is mainly describe the topological order phase, namely the Kitaev-Toric code topological order, which is a Z2 topological order. And you see this model, this simple model, the ground state of this simple model also simply, you can write down the wave function, ground state wave function, for this toric code model. It's just a superposition of various size of loop configuration, and in this form. So in the phase diagram, the toric code wave function is actually a fixed point wave function, because if you look at local operator correlation function, you will find the correlation length is zero. So you cannot use this wave function to consider the quantum phase transition. And also there's no tuning parameter in this wave function. So in order to consider the topological quantum phase transition out of this topological phase, we have to deform this original fixed point wave function. One way is we use this form. We propose some people propose this form to deform this toric wave function. In this form, we also have hx, hz. The roles of these two parameter play actually look like similar to the perturbation term in the Hamiltonian, but not exactly equivalent. That's the same because these two terms is in the wave function instead of in the model Hamiltonian.
What is this sigma ij? Like two. What is
This operator.
Yeah. What is
This is a spin operator
Yeah,
of the
but-
toric code sitting on the edge. Sitting on the edge.
this? Okay.
Sitting on the edge, yeah. And you see, this your boss group have already considered this deformed wave function, and from this deformed wave function, people say one can tuning this two parameter and also can get the E condensing phase transition or M condensing phase transition out of this deformed wave function. Just but the long-standing puzzle is still haven't well answered. So we use a similar deformed wave function, and also this hx hz field we slightly combine them into this h and theta parameter in order to get this simple phase diagram. And I should say, for this deformed wave function, if you, for example, if you just on this hz axis, along this hz axis, hx is equal to 0. When the hz is comparably smaller, you can map this. You can find this deformed wave function actually equivalent to 2D. To the previous model, the previous perturbed toric code Hamiltonian, and also this transition is Ising 2D Ising phase transition, and the previous tensor-network calculation has done this is some result of their work of their results. You can see here clearly. They see there's a continuous phase transition, and also along this vertical line, and they notice there are continuous phase transition along this electromagnetic dual line. However, as I said, actually both phases along this two lines are topological trivial. From the Landau theory, you will get there should be no phase transition at all. But here, the numerical calculation clearly indicate there is a continuous phase transition. But what the nature of this continuous phase transition, they don't know. From the numerical point of view, they cannot determine the nature of the phase transition.
What was the Hamiltonian that you studied?
Actually, there's no Hamiltonian at all. We just have this deformed wave function, And you know, I think afterwards I will show how to calculate the phase diagram from the deformed wave function. Yeah, maybe.
No, I mean for this paper, for this one.
Yeah, actually the methods we use are very similar. Yeah, they just consider the norm of the wave function, and rewrite this norm into a partition, a classical model of the partition function of a classical model, and calculate that partition function. You see. But yeah, this here I will introduce our work on this problem. Yeah, our contribution to this problem is we rewrite the previous deformed wave function into a tensor network wave function. Here I show you here. You see the toric model is defined on a square lattice. The Pauli spin sitting on the edge of the square lattice. But here we have introduced the auxiliary spin sitting on the vertices, this S operator. And the previous deformed wave function, we rewrite it, and under this gauge constraint for the auxiliary spin into this form. This is previous deformed projector operator, and you see, in particular, you should look at this term. This term clearly indicates the interaction between the physical spin and the auxiliary spin. They are coupled together here in this term. And then we consider the norm of the wave function analogous to the plasma treatment for the Loffian wave function. We write this norm into this form. You can immediately say this is a classical Ashken-Taylor model. The form like this, you see, and this norm of the deformed wave function in the presence of tensor network representation look like this double layer tensor network. It's a double layer tensor network. Here we just integrate out the physical spin sigma Pauli spin, and we left the S operator and the T operator, which are separately described the top layer and down layer auxiliary degree freedom. You see.
I'm sorry, what is the PS and PT?
Yeah, this is just the global projection operator, which just in fact the boundary condition of the statistical model.
Then where the HG and HX goes in the norm of the wave function?
Sorry.
HG and HX should appear in the norm of the wave function, no?
This come into this J and J4 term.
Ah,
Yeah.
okay. I see.
So this is the classical Ashken-Taylor model. This J you have this form in a function of H and theta, and J4 is also have a different form of. And actually, you may look at this model very simple, because it's just like a two-layer of easy model, and with interlayer coupling with these four spin terms. Yeah, this model, this statistical model, actually is also an exactly solvable model only along the self-dual line, and except this self-dual line, people can use other numerical methods to get the transition line away from the self-dual line. So this is the 4-phase diagram for the classical Ashken-Taylor model. In this model, you clearly see there are 3 different phases. One is this paramagnet phase sitting on this corner, and another phase sitting in this corner called Baxter phase, which is long-range order phase. In terms, this S and T operator, ferromagnet order, and also around this corner, there's a new phase called partial order phase, which just interlayer order without interlayer order. This is called partial order phase. And between the partial order phase and the paramagnet phase, second Ising continuous phase transition, and also the partial order phase for the partial order phase to the Baxter order phase. Except that between the Baxter phase and the paramagnet phase, there is a KT transition line. There's a KT transition line, which has a central charge equal to 1. And also, the Baxter phase and the paramagnet phase are due each other. So, and also you see there's a dotted line. This dotted line indicates, this parameter on the dotted line corresponding to Q equal to 4-state pulse model. As you know, 4-state pulse model has a 2-phase, order phase and disorder phase. The phase transition is a KT transition, just has a point. But along this continuous phase transition line, the effective field theory is given by the Z2 orbifold Gaussian scalar field theory with a parameter by the radius r. This r is you see as a function of h, because in this line the theta is fixed to the pi over 4. So just a function of h. Exact at this point, this 4-state pulse. This point, this r equal to 2 square 2, and at this point, oh sorry, I should mention this. This boundary line of this phase diagram corresponding to J4 equal to 0. So this boundary line describes 2 decoupled Ising model. 2 decoupled Ising model is you know this 2-dimensional classical model has a continuous phase transition. You see.
Excuse me, maybe I just missed. The model you first referred to has first order phase transition as
No. I didn't find first order phase transition. I just say the problem I studied connected to another problem.
So the model is different.
The model is different.
I see.
Yeah.
Okay.
Yeah, slightly different. But there is a connection between the model I consider and the model previously I mentioned. Yeah. In the later I will talk about that.
So this red line, you say it's Costello-Zales transition, is not Ashken-Taylor universality class?
Costello phase transition, because in the Ashken-Taylor model, you have a continuous transition line which is a Costello.
Does it actually? I'm wondering if Ashkenazi model just a spin model on a specific lattice or no? It's just a Hamiltonian view.
Yeah, it's just a Hamiltonian like this one. This is a well-studied model in statistical physics. You see, I adapted this phase diagram from Cardinal's 1980s paper. And, yeah. This is a well-known result, actually. But here I just relate the problem we want to study with this well-known classical model.
You want to solve your problem on a square lattice.
Yeah,
You want to solve this Hamiltonian on a square lattice.
yeah. So this is some contents about the two orbit for CFT, and in two-dimensional case, the action for this CFT theory usually write in this form, and there's a parameter can be changed. You know, this parameter G actually is a function of the radius r. You know, maybe I don't need to go to the detail about this. So you know, after that we established a correspondence between the quantum model and the classical model. That's quite important. That's very important things actually. You see, previously we know those anionic excitation in the toric cold phase, this electric charge and magnetic flux, and can be written in terms this Ising spin operator of the Ashken-Taylor model, this SZ and TZ, something like that. And also you can check the statistics between the electric charge and the magnetic flux. They satisfy this semiotic statistics. And also you can also calculate the spin-spin correlation function in the quantum model. In the quantum model, by relate this correlation function to the operator in the classical statistical model, and clearly you see that this local operator in the quantum model is no longer the local operator in the classical model anymore. So
which part is non-local? I don't see it.
you see here that this is a quantum operator in the quantum model,
Yes.
and when you transfer to the classical model, becomes a sigma tilde. It's a sigma tilde in terms S and the T operator. This is the exact expression for these three different components.
And T, what does T look like?
You see, this partition function, the classical partition function actually calculates a two-layer Ising model. You see, the top layer Ising I call T, the bottom layer Ising spin I call S.
Then isn't this still local? Is it non-local?
Yeah, I still don't see.
Yeah, become non-local, because
It's written in I and J.
Sorry.
So only I and J
Yeah.
is involved. So in this.
Oh, sorry. Maybe I didn't make it very accurate. Yeah, it become not a simple correspondence. Yeah, not simple. Yeah. Do you have any further question.
Yeah, I mean, this, basically the same question. I mean, I didn't clearly see which part of this expression is gives you non-local property.
Non-local maybe more maybe not accurate. Yeah, maybe not accurate. Oh, maybe you can. If you look at this form, this is non-local. This non-local form. There's a magnetic flux operator in terms of a string of this domain wall operator of the bottom layer Ising spin. Yeah. Are there any questions? I should. So along the electromagnetic self-dual line, clearly we have a phase transition between the Z2 toric phase and the Gapless Coulomb phase. And in this Gapless Coulomb phase, we have a quasi-Lagrange order. The order parameter is the pair of electric charge. You can calculate this order parameter. You see H less the HC, which this order parameter is 0, and when H is larger than 0, this order parameter behaves Power law-like. And also you can calculate the correlation function of the pair of electric charge. And you see this quasi-Lagrange order behavior in the Coulomb gas phase. So, and also you can see, because it's a Coulomb gapless phase, there's a conformal field theory descriptions. You can calculate the scaling dimension of generic anion correlator when you're across this phase transition. You can see that clearly there's a scaling dimension in this phase, and also at the two ending point. One is this the four-state pulse model point, and we get this finite size spectrum for the four-state pulse model, and also another ending point is the two decoupled Ising model. We also get this CFT finite size.
Excuse me, I have a question.
Yeah.
Between A and B, did you calculate the conformal?
Conformal tau, yeah. But here we calculate the transfer operator, transfer matrix operator eigenvalue spectrum, which connected to the corresponding to this finite size excitation spectrum of the CFT. Exactly. And away from the self-dual line, since we already have the exact wave function, in order to determine the phase boundary, we use this quantum fidelity matrix. We can determine the boundary of the continuum phase transition. These are two different fidelity susceptibility, and indicated there's two different two Ising transition line and this KT transition line here. So after that we can get the phase diagram for the deform wave function of the toric phase, the complete phase diagram. And this phase diagram actually comparable to the phase diagram of the Ashken-Taylor model, but the meaning of each phase are slightly different, and also the properties are different. So the difference is sorry. The two important properties I should point out. In all phase diagram, in order to answer your question, in all phase diagram, all the phase transition line are described by a two-dimensional time-independent conformal symmetry the series instead of a 2 plus 1 conformal field theory. This is a more important thing, which people call is this conformal quantum critical point or quantum critical line, which is different from the conventional wisdom. You know, in the conventional wisdom, you will expect for two-dimensional quantum system, the phase transition in this system should be described by 2 plus 1 effective field theory. But here we just get 2 plus 0, and also this there's a special continuum phase transition line separated two seemingly non-topological phase.
I have a comment.
Yeah.
I think what you study is just Einstein carry, which has nothing to do with Kitaev model itself, Kitaev Victoria code.
I will comment on this this point in the following. Yeah. So the question, in order to answer the Tao Xiang's questions, the asked question, so I compared the wave function approach and Hamiltonian approach. Clearly, there are these are two different approaches, and the results also are slightly different. So, as I say, in the present result, both transition, those three continuum phase transition lines are described by 2 plus 0 quantum field theory. But in the Hamiltonian approach here, these two Ising transition lines are three-dimensional line. It's not a two-dimensional line. So we believe that, for example, along this self-dual line, when we increase the bound dimension of this double-layer tensor network, we will expect this Gapless Coulomb state will get confined, and this continuum phase transition line of this caustic solids type will become the first-order line. And also this Ising, two-dimensional Ising universality transition line will also get will become the three-dimensional Ising universality class. This so we can draw a figure like this. Yeah, in order to consider the phase transition between this topological phase and this trio phase, actually we can have two different approach. One is so-called this Hamiltonian deformation approach, and another is this wave function approach. These two different approach will give us two different fixed point, characterizing the phase transition between these two phases. However, there is also another path, RG flow path, inside this picture, which connect these two fixed points. I think this idea is we have developed further. And next time, if I have opportunity, I will show you how to drive our results from this 2D fixed point to the 3D fixed point. Yeah, we already have some development in here. So although they are two different way and two different, slightly different type of phase diagram, but they are closely connected to each other. You can regard it in the Hilbert phase space, physical space. This 2D phase diagram is just a corner of this this wave function physical space. And when we expand the bound dimension, we can recover this three-dimensional phase this three-dimensional phase transition. Yeah. Sorry, use too much time. So next, let's make a summary. So we develop a novel quantum phase transition approach, in particular around the electric magnetic self-dual line, and carefully consider the topological phase transition out of the Z2 topological order phase. And this approach provides a potential new route to tackle a long-standing puzzle. And also our approach can be generalized to Zn and the non-abelian topological phase. Regarding the non-topological phase, actually recently we already put another paper on the web, on the archive, to consider, the Fibonacci topological order phase, the topological phase transition associated with the Fibonacci topological phase. This as you know, this is a non-abelian topological phase, and we use the same spirit to develop the wave function approach to study the phase transition out of the Fibonacci topological order phase. But in this case, you see the deform wave function we have for the Fibonacci topological phase is a is in this form, which in terms of so-called dramatic polynomial function here is slightly complicated. And also you see that the norm of the wave function now become two coupled phi square Gauss model. This phi is the golden ratio for the Fibonacci annual. It's golden ratio. So in this actually this is a new type of statistical classical model. We have used the tensor-network to get the full phase diagram for this partition function. Here's the result. You will see in this phase diagram, maybe you should. I use slightly different notation here. I use h and h hat. This is a two parameter. So the phase diagram also h hat, h is this parameter here. But you see in this phase diagram there's a double Fibonacci annual phase and other two non-topological phase, and between these two non-topological phase there's a self-dual line. Along the self-dual line, there's a larger part, the majority part of self-dual line is the first order transition line. At the tri-critical point, they separate into a two continuous phase transition line. The corresponding conformal field theory describing this continuous phase transition with central charge 40 over 50. This CFT. The novel things is around this tri-critical point. This tri-critical point is described by a central charge equal to 27 over 20, which is coset CFT theory. And with the coset CFT theory tell us exactly at this tri-critical point, there's a fractional supersymmetry because this coset theory involves these three paraformula in it. The excitation in this at this tri-critical point. Okay, I already used up my time. So that's all for my talk. Thank you very much. Please.
So you said that the 2D Ising transition in machine teller model is unstable towards the 3D Ising
Yes.
transition.
Yeah.
And what happens about the KT transition point?
The KT is very delicate. In the actually,
Is there near similar instability towards another
no,
point?
no,
So
no.
what is that?
The KT transition is look like a marginal situation. So when
so you believe that the KT transition, there's a
for
how to say that the criticality is stable in 2+1 dimensional system?
unstable.
Unstable.
Yeah, unstable.
Then what
For
is
for
the
example,
answer?
my intuition comes from the following. If you here you can think about a generalized Ashken-Taylor model. For example, you consider 3 layers of Ising model and coupled together also with a similar interaction. In that 3-layer coupled Ising model or generalized Ashken-Taylor model, the KT transition line becomes first order phase transition line.
So there's a-
This is an old result
then-
back to the 1990s, early 90s. Yeah, people already exact solvable result. Yeah. So in this sense, this KT transition line is just sitting on the marginal situation instead of.
How about there's a multi-critical point? I'm asking.
You mean this is a multi-critical point?
Yeah. So what is your answer?
This a little bit difficult to. At the moment, I cannot tell you this satisfied answer, but we will get a clear result in near future, I think. Yeah. Yeah, you're quite right. Around this tri-critical point is very important and very delicate. Yeah. Yeah.
So this projection operator 1 plus h sigma x plus sigma y. It looks to me like lowest order Taylor expansion from Kurzweiler term. So I can imagine that you put the segment totem into an exponential form.
Oh, you can write this form into an exponential form because this is just the Pauli matrix.
Right. If you
The sigma square for each component is 1. So you can write in terms of exponential form h sigma z and h sigma plus h sigma x. Yeah.
This is quite important for getting a stat map description of the overlap. Is that right?
Sorry, what is the stack map?
Statistical mechanics interpretation to the overlap. Is that directly related to the fact you can rewrite your projection operator into exponential of some operator?
No, it doesn't have.
Okay.
It doesn't have.
The refunction you wrote is actually we call the pass.
I see. I see. I see.
Can you comment on this sort of connection between the two approaches? Because in
Okay.
sort of my experience, the two approaches are completely different, the wave function approach and the Hamiltonian approach.
Yes, yes.
Well, we actually sort of studied this model where we just added like an extra parameter in this trial wave function, and we just variationally optimized, and then you see that you basically just avoid this easing transition kind of thing in this wave function, and the transition is completely different if you do it on a sort of Hamiltonian.
Actually, maybe you already know that for the when we have this deform wave function, in principle we can calculate the parent Hamiltonian corresponding to this deform wave function.
This one,
yeah, which is quite different from the Hamiltonian I introduced early in my talk. That's more complicated than that Hamiltonian.
Yes.
So this is two different approach to consider the phase transition between two same phase, two different phase, the two topological order phase and the trivial phase.
Well, but in my experience, the physics is also completely different. The kind of physics that you
No. The physics, the criticality may be related, although the Hamiltonian form are completely different. But the criticality are the same, or closely related.
But there's like one is like 2D criticality, and the other one is 3D. So they must be
Actually, we can generalize this procedure into a 3D, yeah, which is undergoing work. Yeah.
Actually, I'm not familiar with this literature, but the mechanical result of the first order nature of the transition. I mean, it's not your work, but I mean, is this to what extent this is, I mean, trustworthy, reliable?
Yeah, this transition actually is quite interesting. Yeah, maybe you know this is so-called deconfined quantum criticality things. This stuff, you know. From the Landau phase transition, you first expect this should be a first order instead of continuous phase transition.
I see.
But
so you think that I mean maybe this so first order phase transition might be actually to second order phase transition. That's what you're suggesting.
No. On the special condition, it will becomes a deconfined continuous phase transition. Yeah.
So in their case, in the case where they observe the first order phase transition, it is really first order phase transition.
Yes. But that phase transition is a 3D type. Yeah.
Is it just because here you have continuous phase transition just because you do not have any entropy? You stay at ground state. So there's no computation.
Okay. We will look at more carefully to in order to get the first order phase transition from 2 plus 0 to the 2 plus 1. Yeah, this is the second step of our research project, I think. We will answer that question in the future. Yeah. Okay. Please.
Is it possible to, for example, by adding some extra terms to connect the dual phases without phase transitions? Yeah, you mentioned it's possible.
From which phase to which phase?
From the confining phase to its phase.
Yeah, you can adding another term. That in that way somehow you extend the phase diagram from 2-dimensional to 3D. Yeah.
So it's possible.
Yeah, that's right. Okay. Any other question, comment? Okay, if not, thanks again. Yeah.